Dr. Ken here with you. AC Practice Knowledge Assessment T1 to T7 Part 2. As I mentioned in the previous video, T1 to T7 is just the topic points from the National Training Package. So again, a reminder how the videos work. There's 4 slides for each question. So the first slide, we pose the question, and once we have the actual question, we then pause to give you an opportunity. Well, actually, you have to do the pausing. Pause the video, have a go at the question. Then when the next time you run the video, I will give you a hint. And again, you pause at the hint screen and have a second go at the question if you've not been able to understand it or get the question right. And then finally, the fourth screen, I actually give you the answer and explain why that is the particular answer if I can. So let's continue on. So here's question 11. Determine the capacitive reactance of a 7 microfarad capacitor connected to a 220 volt 50 hertz supply. So you need to pause the video here while you work that out. Well, welcome back. Let's now give you a hint. So if you actually just wrote out the formula for capacitive reactance, that's what the formula is that you're going to need. And there should be enough information there in the question for you to be able to determine the capacitive reactance from the formula. So again, if you've not been able to do that now by pausing the video. Well, welcome back to the video. Let's now look at the answer. And the formula for capacitive reactance, XC equals 1 on 2 pi FC. So in this particular case, we're going to have XC is going to be 1 on 2 pi, 50 for 50 hertz, 7 for 7 microfarads, and times 10 to the minus 6 for micros. I'll just put the pen on. You can see we came to an answer of 455. Don't forget, when you're putting this into your calculator, to put this part in parentheses, so this part is done before the inversion. The 50 is our frequency, so that has simply come from this value here. And we've got microfarads up here, so that's where the 7 times 10 to the minus 6 comes from. And the rest is straightforward. From there, it's just a matter of doing the mathematics with your calculator. 12, next question. Determine the inductive reactance of a 92 millihenry inductor connected to a 220 volt 60 hertz supply. So this time, determine the inductive reactance. So time to pause the video here while you select the appropriate formula and do some calculating. Well, welcome back. Let's give you a hint. So again, the hint is reasonably straightforward. Just select the appropriate formula for inductive reactance from your formula sheet. Put the numbers into it and do the calculation. If you haven't already done that, so pause the video and give that a go. Okay, let's now move on to the answer. So again, the formula for inductive reactance, XL, is equal to 2 pi FL. And I'll just turn my screen pen pointer on. And again, we're going to put in 60 and 92. The 60, this time we've got 60 hertz for our frequency. So that's where the 60 comes from. And we've got 92 millihenries. So that's 92 times 10 to the minus 3. Again, making sure we put all that in the right order into our calculator, and you should end up with 34.7 ohms is the inductive reactance XL. So question 13 now, determine what frequency a 69 millihenry inductor has when the inductive reactance of 60 ohms. So what's the frequency when the inductor has an inductive reactance of 60 ohms? So pause here. Okay, let's now move through to the hint. So we're going to need the formula for inductive reactance, which we should have used in the previous problem, but this time you need to actually transpose it for F for the frequency. So again, if you didn't realize that, pause the video here and have a go at transposing your formula and working out the frequency. Okay, moving on. So let's look at the answer. Again, standard formula 2 pi FL for the inductive reactance. We transpose for F and we get XL divided by 2 pi FL. And we put the numbers into the formula and we should end up with a frequency of 1,384. And yes, just again a reminder to make sure that you actually put parentheses around here to make sure those multiplications happen before you do the division. So question 14, which phrase best describes a particular inductor? So which of these phrases best describes a practical inductor? So we're describing a practical inductor, not a pure inductor, as a hint already. So an inductor and a capacitor in series, a resistor and an inductor in parallel, a resistor and an inductor in series, a resistor in series with a capacitor. So pause the video here while you have a think about that. Well, welcome back. Let's now give you a hint. So our hint is a practical inductor has two characteristics. So what are they and what is their relationship? There's two very important parts to know which characteristics and what's their relationship with each other. Okay, let's now move on to the answer. And straight away, I'll just turn my pen on. The first one is an inductor and a capacitor in series. Well, capacitors have got nothing to do with practical inductors. We've got here a resistor and an inductor. Yes, that sounds good. But when I said the relationship was a series relationship, so we can eliminate that one. The third one is a resistor and an inductor connected in series, so obviously that's the correct answer. And a resistor in series with a capacitor, again, got nothing to do with capacitors, so pretty easy to eliminate that one. So question 15 now. Below is a resistive AC circuit. What will occur when an inductor is added in series with the resistor? So at the moment we've got a voltage at 60 Hertz, an AC voltage, and it's connected with a resistor across it. What happens if we add an inductor in series? What best describes what will happen? The voltage across the resistor will go up, the line current will increase, the phase angle will decrease, and the supply frequency will go up. They're the four possibilities. So let's pause there. So let's now look at the hint. So what's the hint? Draw the complete circuit. Think about it. Is the overall reactance going to go up or down? So what do you think might happen? So let's move on to the answer. The answer is the phase angle will increase. So if you did what as the hint suggested, and we put the inductor in series, here's our inductor in series here. And if I was to draw a quick little phasor diagram, here would be the voltage across my resistor. Here would be the voltage across my inductor. So voltage across the resistor, voltage across the inductor. So what's going to happen? Look, all of a sudden, I have a phase angle in here. When I had the resistor only, there was no phase angle. So the voltage across the resistor will go up? No, because we're going to get a voltage across the inductor, and we're going to get a voltage across the resistor. So the resistor voltage will actually go down. So that one's wrong. The line current will increase. Well, no, we've added some XC here, so it's in series with the resistor, so the total resistance effectively of the circuit will go up, so the current must go down, so the overall current has got to go down. So current will increase? No, not possible. Phase angle will increase? Well, we saw that from our little diagram there. And the supply frequency will go up? Well, no, the supply frequency obviously is going to stay at 60 Hertz. It's not going to change. So with a little bit of elimination and drawing the circuit, and maybe even drawing a little bit of a phasor diagram, you quickly answer the question. So question 16 now. To meet the requirements of AS3000, a capacitor of more than 0.5 of a microfarad must be provided with what? Option 1, a control system. Option 2, a protection system. Option 3, a current limiting system. And option 4, a discharge path. So have a think about that. Well, let's move on now and have a look at the hint. The hint was pretty obvious. Just go and look up AS3000. Remember, the capacitors hold charge even when isolated. So this is what this rule is all about. So if you go to your AS3000, go straight to the index at the back, look up capacitors. There will be a part to look up. Go and look up the appropriate rule. So you can pause here while you go and look up the appropriate rule. So welcome back. Let's have a look at the answer. The answer is to provide a discharge path. So what we have to do with a capacitor is here's our big capacitor, and it's all charged up because we have an AC circuit of some kind connected to it. I'll just put a switch in there, and we'll put a voltage AC across it. So an AC voltage of some kind. So AC, but let's say the voltage across here gets up as high as, say, 300 volts while the switch is closed. Soon as that switch opens, so we open the switch, guess what? The voltage still stays at 300 volts across the capacitor, and it can stay there for a long time. So the way we solve the problem is we simply put a resistor in parallel across the capacitor, and it's normally something in the order of 100k, something that large. So 100k ohms, and that provides a discharge path through the resistor whenever the supply has been isolated. It may take 10 or 15 minutes to discharge, but that's okay, and that's what has to be done. So whenever you see large capacitors in industrial applications, you'll quite often see a resistor connected across it because you've got to provide a discharge path. So question 17 now. Below is a resistive AC circuit. What will occur when a capacitor is added in series? So we've got a resistive circuit again. What will occur when we put a capacitor or add a capacitor in series? The four options are: the voltage across the resistor will go up, the line current will lead the supply voltage, the phase angle will decrease, or the circuit impedance will decrease. So they're your choices. So let's pause there while you have a think about it. Well, welcome back. Let's have a look at the hint. So, draw the complete circuit, think about it, the overall reactance and the relationships between the voltages and the currents. Again, maybe even a little phasor diagram. So pause here if you need to, have another rethink. So let's move on to the answer. So the answer is the line current will lead the supply voltage. So let's do a little diagram. This time we've added a capacitor in series. So here's my capacitor. Just very roughly add him in series. So voltage across the resistor will go up. Well, no, we're going to get some voltage drop across the capacitor. We're going to get some voltage drop across the resistor. Therefore, no, the voltage drop across the resistor is not going to go up, so we can eliminate that one. The line current will lead the supply voltage is the correct answer. The phase angle will decrease. Well, before we put the capacitor in, here was the phase angle for the voltage across the resistor. Here's the voltage across the resistor. Yep, so no, that's not going to happen. So the phase angle will decrease. Probably not. It's probably going to increase. The circuit impedance will decrease. Well, no, the overall current will go down because we've added some more reactance here. We've added a whole heap of XC. So our current, our I total, by definition has to go down. So the circuit impedance will decrease? No, the circuit impedance will actually increase. So we can eliminate that one, and we are left with this one here. And if we have this as the voltage, the current will lead the supply. So if we draw our current up here, so our current in the capacitor IC is in this direction, and remember our phasor diagram is rotating in an anti-clockwise direction, therefore the current will be leading the voltage by 90 degrees. So this time, question 18, calculate the impedance of the circuit below. So we've got 200 volts at 60 Hertz. We've got a capacitor with an XC of 18 ohms and a resistor of 34 ohms, and four possible answers: 52 ohms, 16 ohms, 61 ohms, or 38 ohms. Pause here while you think about it and calculate out what the answer will be. Well, welcome back. Let's have a look at the hint. So pause here while we look at the hint. So again, draw an impedance triangle is the hint. So once you draw an impedance triangle, the formula you might need will probably trigger in your brain. So pause here. Okay, welcome back. Let's have a look at the answer. So the answer is 38 ohms. How did we get to our 38 ohms? And if you drew an impedance triangle, you would have had the R here and the XC here. So our 18 and our 34, and the hypotenuse of the triangle is the overall impedance of the circuit. So we're asked to calculate impedance up here, Z. So simply was 18 squared plus 34 squared, and then take the square root of all of that, and that equals 38. Moving on now to question 19. A motor stator's internal resistance is measured at 53 ohms and the reactance is measured at 38 ohms. Determine the current drawn at 220 volts, 50 hertz supply. So pause here. A motor stator, internal resistance of 53 ohms, reactance of 38. Determine what the current is, 220 volts at 50 hertz supply. Well, welcome back. Let's have a look at the hint. So again, pause here if you need to. There are two distinct steps here. You have to determine the impedance. So draw an impedance triangle to make sure you get that right. Then use the impedance to calculate the current. So two steps: determine the impedance, use an impedance triangle to get it in your head, and then calculate the current. So if you didn't think of those two steps, pause here and do the calcs. So welcome back. Let's have a look at the answer to number 19. So here's the answer to number 19. Step 1 over there on the left-hand side. We had 38 ohms at 90 degrees to 53 ohms. The resistance and the XL are at 90 degrees to each other. So again, just Pythagoras, 38 squared plus 53 squared. Take the square root of all of that. Gives you 65.2 ohms. So we take that 65.2 ohms, and Ohm's law tells us that the V divided by the Z equals the current. So 220 divided by 65.2 gives us an answer of 3.37 amps. So question 20. Determine the phase angle between a pure capacitor and a pure inductor in an RLC AC circuit. So the question is, determine the phase angle between a pure capacitor and a pure inductor in an RLC AC circuit. So we've got 4 possible answers: 90 degrees, 180 degrees, 45 degrees, or 0 degrees. So pause here, have a think about what would be the answer. So we're back again, time for a hint, of course. So the hint is draw a phasor diagram. If you're not sure, if you cannot picture it in your head, and most people can't picture it in their head, so draw a phasor diagram. It'll create a picture in your head, which is a good thing. So let's now move on to the answer. And I've drawn a phasor diagram here for us. So resistance is always on the reference. Capacitance leads the reference by 90 degrees and inductance lags it by 90 degrees. But the relationship between the capacitance and the inductance, you can see it here, is 180 degrees. So let's turn my pen on. It's not 90 degrees, obviously. 180 is correct. Certainly nowhere near 45. And of course, things are well out of phase, so it's not in phase at 0 degrees. So the only possible answer was the 180 degrees. So this brings us to the end of part 2. So again, thanks for listening. I hope you've gained some improvement of your knowledge and skills around alternating AC current. This is topics 1 to 7 in the National Training Package, and this was video number 2 of 3.